All right, good afternoon, everybody. So it is now my great pleasure to introduce Dr. Carl Williams, who will be, is louder? I can hear myself. Can you hear me? Is this okay now? It's a little bit better. You can come up forward. So Carl Williams will be giving the 2019 PQI public lecture. I'd like to tell you a little bit about Dr. Williams. So he is currently the acting director of the Physical Measurement Laboratory at NIST. He's also an adjunct professor in the physics department at the University of Maryland. And at NIST, he directs the Quantum Information Program and helps lead the National Strategic Computing Initiative. Dr. Williams received his BA in physics at Rice University, and then his PhD at the University of Chicago. In 1998, when Bill Phillips won the Nobel Prize, he recruited Carl Williams to NIST, and Carl quickly rose up in the ranks. He was the coordinator of the NIST Quantum Information Program starting in the year 2000. He became the chief of the Atomic Physics Division at the NIST Physics Laboratory in 2004. He became the chief of the Quantum Measurement Division of the NIST Physical Measurement Laboratory in 2011. So in 2006, Carl Williams helped to establish the Joint Quantum Institute. He was founding co-director. So JQI is joint between NIST and the University of Maryland, and so he was directing from the NIST side. So he held that position until 2011. He is also a founding fellow of the Joint Center for Quantum Information and Computer Science, or QUICS. So he has had many other leadership activities outside of NIST. So he was a senior policy analyst at OSTP, the Office of Science and Technology Policy, from April 2008 through July of 2010, spanning 2 different administrations. So he's a fellow of the American Physical Society, the AAAS, Washington Academy of Science, and he has won several awards for excellence in government service, the Arthur Fleming Award in 2005, also the Department of Commerce Silver Medal in 2003 for his leadership in the Quantum Information Program at NIST, and the Department of Commerce Gold Medal for science in 2008 for scientific contributions. He's also the associate editor of the Journal of Quantum Information and Computation, and continues to publish to this day. I should also say that he's a great friend and also a supporter of the Pittsburgh Quantum Institute. He came here 2 years ago and gave a wonderful impromptu talk after our banquet. And so it was a very easy decision to invite him, and of course it's also a very timely one to invite him here to tell us about this revolution in metrology that involves quantum mechanics in a very deep way, and is really also sort of signifies this transition from the first quantum revolution to the second quantum revolution. So the title of his talk is From Platinum to Planck, the biggest revolution in metrology since the French Revolution. So please give a warm welcome for Dr. Carl Williams.
Thank you, Jeremy. So this is going to be part history and part science. And so I'm going to talk about the redefinition of the Treaty of the Meter, and you will explain, I'll explain the title as we go along. As many of you may not know, we've been a metric nation since we signed the treaty in 1876. You may not believe that, but in fact, we outlawed those states who tried to forbid the use of the metric system in 1866. But effectively, the Treaty of the Meter is one of the oldest treaties around. It was established in 1875, and the U.S. officially signed it in 1878, but we were one of the original signatories. But of course, the basis of the metric system goes all the way back to 1799. And the idea was not to have the units of measurements based upon somebody, but to base upon nature. And so we'll see how this goes, and we'll see where we're going to today. So most of you, part of signing of the treaty was they set up an international holding organization that just crossed the Seine River from Paris in Severn. So this is the International Bureau of Weights and Measures. And of course, that bureau is overseen by a committee that consists of 18 members from the that are designated by the member states. And then, of course, there's the General Conference of Weights and Measures, which I will come back to as I go through the talk. So the thing is what I do, what my lab does, and you may not realize it, is that the Physical Measurement Laboratory at NIST is responsible for all physical measurements in the United States. Almost anything that is measured eventually traces back to my organization. And you may not see it, but that infrastructure that lies under it is everywhere. And so we do, and we realize things like resistance over 22 orders of magnitude. We realize force over about 21 orders of magnitude. And you say, well, why do you do this? What's the purpose and everything else? It's so that everybody knows and can agree upon what they're measuring. Because if you go back before the Treaty of the Meter, you know, you can find little instruments where the inch in one country was compared to the inch in another country. And I will tell you, you could make money by buying short, buying long and selling short. And so it really was a revolution to come up with the metric system and everything else. We realize it and we practice it. This is what we do as a lab as a whole. And to do that, we have to do a lot of basic research, but we also do a lot of very applied and calibration services. And I hope by the time I'm done that I convince you that metrology is what makes everything happen. And I know it may sound odd to you that this is the case, but it is necessary for scientific discovery. If you can't measure it, you can't make it, and industry depends upon it. And in fact, part of what pushes our needs is the highest tech industry and their needs. So again, you can see pictures where Boeing is required by law to break the wings off of any new aircraft it has. So you can see it increasing the pressure on its wings until those wings pop off the 788. And all those orange force transducers trace back to NIST. In fact, they sent us about 20 of them prior to them doing that test because they want to be sure if that plane ever goes down and the wings break off, that it passed. So again, we have a machine at NIST that basically does 1 million foot-pounds of 4.54 meganewtons. And it does it to a few parts in 10 to the 5th. That's not an easy job to do. Moreover, in this country, measurements are based in the Constitution. The federal role is established in Article 1. Now, I'm going to talk about this today because on the 20th of May, 1 month and 2 days from now, the biggest revolution in metrology will occur when it becomes official that the redefinition has taken place. And I'm going to explain the redefinition of the Treaty of the Meter and what we have done. So the revolution will be a change to the metric system. At the moment, there are these 7 base units: the mole, the candela, the kilogram, the meter, the second, the ampere, and the kelvin. And when we are done, there will be a bunch of defining constants. Now, I'm going to ask one simple question because it's always fun to take exam questions along the ways. How many constants today are actually fixed? Does anybody know? Can anybody guess? Can somebody name me one constant that's fixed today? Huh? C. C is fixed because in 1983, and I will walk through this, we redefine the meter in terms of the speed of light. And of course, today, epsilon naught and mu naught are fixed too, and we're going to screw those up in the process of doing what we are doing. But that's just a detail. So on the 16th of November in Versailles, there was a vote by the treaty members unanimously to approve the redefinition to become effective on the 20th of May. The 20th of May chosen because that is the anniversary of the signing, the 144th year of the signing of the Treaty of the Meter. So to understand how all this is possible, I will attempt to bring you a little brief history of length, because length is already defined by C. So, you know, in the old days, people defined length by the human body. And of course, this would be great if all of us were identical. It was convenient, but not very consistent. A short fabric merchant might sell you a smaller length of fabric than you had expected. And even in the days when miniskirts were not popular, you might end up with one. So the problem was that you could go and select a particular body. And in fact, this was done. The Egyptians did this and basically created a cubit that was based on the Pharaoh's form in hand and was embodied in an artifact. The primary was of granite, pretty good. Secondary were cubits and woods. Recalibration occurred every month under the penalty of death. So you got conformance, at least in Egypt. It is amazing because if you look at the baselines of the pyramid, they're consistent to 0.025%. This is how well they did. That is actually quite amazing. So it shows you that metrology works even all the way back in ancient Egypt. Similar artifacts, sometimes varying from town to town, with common standards for length measurement in Europe. And so here you see one of the NIST scientists looking at the standard fathom-foot or cubit fixed into the wall in the city hall of the city of Regensburg. Unfortunately, you know, it didn't quite agree with the Bavarian unit of length. Common problem. So the metric system came into existence, and when this was done, it was decided that one would just define the distance from the North Pole to the equator along the meridian that passed through Paris as exactly 10,000 kilometers. And so the meter is 1/10,000,000th of the distance from the equator to the pole along a meridian passing through Paris. Now, actually, they got it off by 0.02%, in part because they miscalculated the flattening of the Earth. It was a math mistake, but they did a pretty good job. And so they did this, but then they decided that wasn't very convenient, so they created an artifact that was equivalent to that. Notice they created an artifact, the meter stick. But the idea was that no longer would units of length and measure depend upon a human. It was an attempt to get at those physical limits. So clear definition. They created this meter stick. This is the original meter stick. And following the convention of the Treaty of the Meter, or the International Treaty of the Meter, if you prefer, it was replaced with the following: platinum, iridium, steel rod. And it was a line standard. It wasn't from the end of the rod to the end of the rod. They understood that the ends weren't perfect, so they had to draw lines in them. You will also see that it is kind of H-shaped. And why? Because you can't band it. Because you can't band it, you don't have the problem of curvature that can affect length. They actually did remarkably well at doing this. I mean, this is really quite good. Oh, what happened did I do? Oh, let's go back. Okay, there we go. However, eventually measuring the distance between those two lines became a limitation. In fact, they were down to about 100 nanometers when they redefined. And to tell you the implications of that, that means they might have gotten another factor of 5, 8, maybe an order of magnitude. But the reality was it was running out of steam. Today, the smallest features inside your cell phone are 7, 9 nanometers. And so the de facto distance became inadequate, and they decided to use light. And by adjusting the light in a device like shown, they could make the spot in the center either be dark or light. And as a result, they had something that was sub-wavelength sensitive. Shortly after this, they basically came and realized that you could use, the laser was invented, and that the laser, so you don't need a krypton light, you could use a laser, and the Heaney became the next kind of form for which one could use to create a laser. In fact, laser light was the de facto length of standard. By the 1970s, almost everyone was using iodine-stabilized helium neon lasers to measure length. Why? It was cheaper, faster, more convenient than having an artifact that you'd have to compare and keep under the appropriate thermal control and everything else in order to get your measurements accurate. However, such lengths were not in the official SI meter. They were outside the metric system. So the meter needed to be refined. The obvious choice, define the meter in terms of iodine-stabilized helium neon laser. The brilliant choice was to define the speed of light. And so that was what was done. The meter is the length of light, length of the path traveled by light in vacuum during your time interval of 1/299792458 seconds. Why? Because the speed of light is exactly that in meters per second. And when you define it exactly, it doesn't matter. So what does that mean today? Well, today we have lasers that are sufficiently stable that we can bounce them off that mirror that we left up on the moon, and absence a few corrections for some refraction of light and going through our atmosphere. There's not much atmosphere between the Earth and the moon. We can come back and get an interference fringe and correcting for the aberration due to the atmosphere, which we know how to do today extraordinarily well, which is why all of our telescopes work so well. We can basically instantaneously measure the distance from here to the moon to a fraction of the wavelength of light. Clearly clever. Now, in some ways, you could say those brilliant people foresaw this Nobel Prize because, again, what these people did is created the frequency ruler that allows the full use of that definition forever at any wavelength, anywhere, because we now actually have a way to compare one frequency to another. So the definition of the meter is both brilliant and beautiful. Today, the CGPM is about to do the same beauty to the kilogram. In fact, they voted on this on November 16th at Versailles. So why and how? So let's give a little history of mass. Well, again, you can go back to Mesopotamia. People created objects that were mass standards. When the meter came around, the Treaty of the Meter came around, or in 1793, it was decided to describe a kilogram as being defined as 1 decimeter of water. Now, the question is, what water? And it was Viennese salt water. Well, what Viennese salt water? What temperature? Well, eventually they got the temperature fixed, they did a few other things. But when they were done, they decided, this wasn't very convenient. So let's just take that volume of water and find a mass that is equivalent to it, and we'll call it a kilogram. And of course, they created another artifact. And so that's the original artifact from 1790 that was there. And they then, after the 1875, created a new set of artifacts. And the one I pictured here, I believe, is one of ours. But I believe you will see a picture of Legrand K, or the International Prototype Kilogram, as we walk on through the talk. This is the last artifact in the system of units. So the kilogram is the unit of mass. It is equal to the mass of the International Prototype Kilogram. Today, in the 21st century, a unit of mass is an artifact, a piece of metal made in the 19th century, based on an object made in the 18th century, that spends most of its time in a safe in Paris. Because nobody in their right mind would want to touch it. They might change its mass. Nobody would want to accidentally scratch it. They might change its mass. So you just don't touch it. Oh, we have a mass scale to an artifact that we keep in a safe that we don't use. Clearly, very clever. This is such a scandal that American newspaper comic strips make fun of it. So let's look at a comic. Mr. Serrani, am I right that we have redefined the meter as the distance traveled by light in of a second? Yes, that is because the previous definition based on global distance was inaccurate at best. And we have similarly redefined the second, which has been an approximation of 1/86/400th of a solar day. But now is more accurately defined by oscillations of the CGPM. Correct, very good. Why haven't we changed the definition of a kilogram? We haven't. The official definition is still the mass of the International Prototype Kilogram, an actual lump of stuff that's stored somewhere. Why, that's so unscientific. Exactly. What if someone snuck in and shaved off a piece? Need to lie down. Told you there are ways of getting to it. Well, let me tell you, nobody has snuck in and shaved off a piece of IPK, but its mass is changing nevertheless. And I'm going to show you some of the evidence, and then I'm going to talk to you about the US mass scale and the international mass scale and what happened over the past little more than a decade. So again, all the masses started out together at the same point. These are a bunch of witnesses to the IPK. The IPK is by definition 0 on this line. This is the mass difference as a function of time. Now you will notice that for the longest time, until after the war, we never actually did a comparison with anything. And we realized there's some problem then. And so we waited a little while, and we did another set of comparisons, and we realized, you really should wash the mass before you do it, because even though it's in a safe, it gets dirty, especially because there's paint in there, and it's volatile, and it's coming down, and of course it loses weight. But of course, it's perfect, by definition. So how could it be losing weight when you wash it? It's only going back to its original weight, right? Well, maybe you added something. Maybe you took something off. Who knows? Well, you can see that that's not very good. And so something needed to happen. And of course, you can say it's only 50 micrograms over 150 years. Well, yeah, it's only 50 micrograms over 150 years, or 100 years. But legally, IPK can never change because it is, by definition, a kilogram. So maybe one of those others were right. It doesn't matter. By definition, this is the kilogram. So from the very beginning of time, NIST had two prototypes. We had K4, that's copy 4, and K20, copy 20. Both of those were required originally. K20 becomes our official kilogram for the US. Why K20? Why not K4? Well, in the old days, you put these on ships. You put them on two different ships just in case one of the ships went down, and K20 arrived first. Very simple answer. In 1996, NIST purchased K79, the 79th copy, And in 2008, we purchased K92. However, when K92 arrived, and it came with its certificate and told us just how far off it was from the IPK, and we compared it back to K4 and K20, we said, there's something wrong. And the BIPM told us, no, there's nothing wrong. We said, there's something wrong. They said, no. There can't be anything wrong. So in 2010, we recalibrated K20, and the following year, K4. And because the BIPM is by definition perfect, even though it hasn't put out its prototype from the safe, because nobody would touch it, the US shifted its mass scale by 45 micrograms on a kilogram, required by law to do so. In 2014, as we are pushing on the redefinition, they finally pull IPK out. And what we learn is the BIPM's mass scale is off by 35 micrograms on a kilogram, so we shift back the other direction. Oh, that is within 2 sigma of where we would have been if we'd never shifted at all. Very few people in the world saw this. We could see it, which shows you how well we preserve and maintain our mass scale. We were one of the only NMIs in the world to see it. There were some hints that there was clear hints the Danes saw it. There was hints that at least one other country had seen it. They just didn't want to stand up and go public, that they might be a problem. So you wash it under the rug. This scandalous situation must be fixed. We want to use a beautiful approach used for the meter. To define the meter, we define the speed of light. So what constant do we use to define mass? And so I'm going to walk you through this one. Well, you know, here's a famous equation, E equals mc squared. We all understand the rest mass of an object, the energy of an object, and everything else. I put that equation up there. I gave you another equation also that has Planck's constant in it, E equals h nu, or hf, where that's the energy of a photon of a frequency of light. And of course, we can all in this room probably do a little mathematics and talk about the change in mass of a particle when it emits a photon. And that's that. Now, counting that many photons would be pretty damn hard. So is there another way we can relate mass to Planck's constant? And I'm going to show you how we do this. And so we're going to define Planck's constant allows us to define mass. And I'm going to show you how we do this actually. And I would say originally known as the Watt bounce, named after Brian Kibble, the guy who first suggested this whole approach. Brian Kibble passed away in 2016. And this BIPM consultative committee on units basically renamed the Watt bounce in terms of Brian Kibble in his honor. So let me show you how you turn a mechanical object into a measurement of Planck's constants. So this is a little video that will show you the principles of a bounce, of a Watt bounce working. This is our 4th generation Watt bounce. So everybody knows the 2-pan bounce. You put mass on one side, you start adding mass to the other side, and eventually you can make the thing come into bounce. But one can take a slightly different approach. One can say, if I put a mass on one thing, how much electromagnetic power does it take in a magnetic field that is just using Faraday's law to basically compensate for that mass? And that's one of the 2 approaches that is used. We see that it moves that coil. The coil induces a voltage. We measure the voltage. But that requires you know also the length of wire in the magnetic field. A little problem. So we have a second mode. We go and we move the coil through the magnetic field and induce a current in it, and we measure that current. And of course, it's the same coil wire, it's the same magnetic field. And so effectively, I just used the two principles that all of you know. One, an electric motor, the other, a speaker. Techniques that are used every day. And let me show you how these combine to effectively give you mass and Planck's constant. So as I said, there's a weighing or force mode. And that weighing or force mode basically involves asking what electromagnetic power do I need to compensate for mass falling in gravity in a very uniform magnetic field. Now, it has to be very uniform. And we know our field is uniform to about a part in 10 to the 5th or 10 to the 6th. We've done lots of tests, and we have shims and a few other things. Getting a magnet that is that uniform and that big is part of the problem of doing this. Our first magnet that we had in the previous versions in NIST bounce 2 and 3 were basically superconducting. Then there's the calibration velocity mode, which you can do. And when you can put those two together and you merge the equations, you basically get power, and this is why it was called a Watt bounce. Mechanical power equal to electrical power. So all I've done is built a very sophisticated bounce to equate those two things together. But now let me show you all the tricks. So that's actually a picture of the NIST Kibble bounce. And like I said, what I do, if I put a mass on there, I know velocity from the velocity mode, I know the voltage from the velocity mode and the current from the weighing mode. I basically have this equation along with the value of the local value of gravity. And so the question is, how does this give me Planck's constant? And so this goes back to electrical standards, and I'll come back to those in a moment, but just let me walk you through how this goes. So you use the Josephson and the von Klitzing effect. So again, here is the force mode. There's the velocity mode. That's the equation of equal. That's the things that says why we called it a Watt bounce initially, now called the Kibble bounce. But I know by Ohm's law that current is nothing but V over resistance. And if I have two voltage and a resistance, I can then use the Josephson effect, which defines the volt, and the von Klitzing effect, which defines resistance, and you put all those numbers in, and you end up with the following equations. Oh, this is the equation before the redefinition. We basically took a known mass, and we determined Planck's constant. That known mass had to be traceable back to the IPK, which is why the IPK got brought out in 2014, and they found they had a problem. This was all the international countries pulling it out so we could ensure that we were all traceable back to the IPK. And of course, you just flip the equation around after the redefinition, and I can determine mass directly from Planck's constant. Now, people have described this as one of the most difficult experiments you can create. Why? I'm going to do this at a few parts per billion, actually about 10 parts per billion. But I must measure voltage, current, resistance, length, time, and the local value of G simultaneously to a few parts per billion. Not easy. In fact, we correct for tidal currents. We correct for the season because there's an oscillation there too. Oh, and when that tidal wave occurred down in Indonesia, we saw the mass shift of the Earth and had to remeasure local value of G in our lab as a result. That's how sensitive that instrument is. And you can see how big it is. It is an amazing piece of work. This was the original piece. I show this picture in part because there is the very young Bill Phillips. He worked with that team that built the first Watt bounce, Tom Olson and Ed Williams. He's still at NIST. Barry Taylor is retired but still comes into NIST. Oh, anybody who tries to know what the value of the fundamental constants, you can always thank Barry. Bill Phillips, many of you know, is a Nobel Prize winner. George Jones retired about a year ago. Marv Cage was one of the first people, to actually realize resistance using the von Klitzing constant. And so is an overhand of von Klitzing. This is the modern team who built the Watt bounce. Again, we built that instrument in a period of 18 months and had it up and running and had numbers off of it. Nobody in the world has ever done this in less than a decade except us. Of course, it was our fourth one. It's a beautiful instrument. You can see a bunch of people, and you can see tattoos on their arms. Some of them are not permanent. I will show you what those tattoos are. You know, how dedicated are you? When some of your staff will go and get the number, Stefan Schlaminger actually has the actual value of Planck's constant on his. That arm is Dave Newell, who does the fundamental constants, and those are the defining constants of the new SI. On John Pratt's arm is the actual value NIST measured for Planck's, because he wanted to be sure it was the number we measured. So they're a nice compliment, but it sure shows a level of dedication and everything else. This is the full team, because again, in addition to this, we had to build a vacuum transfer system, because again, kilogram had always been realized in air. The buoyancy correction is quite large. And so we built a vacuum levitation bounce that basically allows us to directly transfer from vacuum to air, and a few other instruments along the way. I should point out, the Watt bounce was not the only way to do that. The other way of doing it was via the so-called Avogadro project, because there's a relationship between the Avogadro constant and Planck's constant. And it can also be done if you can build a ball that has high enough purity silicon-28. That crystal that is sitting there is worth more than $1 million. Took months and months of centrifuges running in Russia to produce the silicon-28 that went into making it. And it is actually a very beautiful thing. But I would argue, notice, I will argue, it can be used to measure Avogadro's constant. But when you're done, it's just an artifact. But that's the way the Germans did it. A final part of the story, and I want to tell you this one because this is the one base unit. NIST realized this once and realized that nobody in their right mind should ever even attempt to realize this. Everybody realizes the volt and resistance and then uses Ohm's law, because the ampere is the current which is in two straight, infinite wires of negligible dimension, exactly 1 meter apart, in a vacuum would produce 2 × 10⁻⁷ newtons per meter. Really? That's a practical definition? If you can't see all the problems with trying to do that realization, it's not a very positive way. So we're going to get rid of that when we fix E. And I've already told you that. So let's come back to electrical quantities. The reality is, in 1990, the International Electrical Union basically said, look, we're done. We're tired of you screwing with our units, because every time Planck's constant changes, E constant, we have to go recalibrate everything. They say, let's just take the value of Planck's and the electric charge as determined in 1990, and we will define exactly these two quantities, RK90 and KJ90. So they fixed the value of the Josephson and von Klitzing constant, because then they didn't have to worry about what was happening when mass changed. They could just ignore it all. And so since 1990, the world's been running with conventional electrical units, not true SI units. And in fact, the volt will shift by about 100 parts per billion. That's the change since 1990. Now, of course, again, there are Nobel Prizes associated with that. Brian Josephson and Klaus von Klitzing. I mention this because the so-called quantum metrological triangle, the electrical triangle, V equals IR, NIST back in the 1990s decided that we would prove this was true. And so we went out and we built a single electron transistor made of aluminum, again using the kind of technology that people like Jeremy would love, and everything else. These aluminum sets, they weren't very good. There was this charge offset noise and everything else, but we worked and we worked and we worked. And we eventually closed the triangle. So first we demonstrated an aluminum set at an uncertainty of 15 parts in a billion, all the way in 1996. And then we closed the triangle to a few parts in about 20 parts per billion. Now, to 1 part per million in 1999. The fact is, no other NMI around the world has ever topped this. There are a number that are underway. They have now better sets out there. We know how to build better sets. And in fact, the best use for a single electron transistor is not to use it as a qubit with spin, but to use it as a single electron transistor, because then I can play more games around this. And they've become a long way in the past 20 years. So this is a demonstration that can be done, and I assume in the next couple of years, one of the NMIs will actually surpass our record that was set more than 20 years ago. 2 more units were redefined. The mole, formerly the amount of substance with the number of entities equal to the number of 12 carbon atoms, 12 grams of carbon, now simply a number. Of course, we screwed up that 12. Okay, a few chemists were upset by that, but of course you could have chosen hydrogen as 1. I mean, in the end, it's just arbitrary. It's just tying microscopic mass scales to global ones. The Kelvin, formerly 1/273.16 of the triple point of water, now we specify the thermal energy per Kelvin of the atomic constituents. That is, we define the Boltzmann constant. So all that is part of the redefinition. Basically, this little chart shows you the old base units and the new ones, because effectively, because the hyperfine frequency of cesium is defined, basically we've set frequency. C is defined, so we've set velocity, H, action, electric charge. They're really not the base units, but from them I can derive all the base units. So a long time has gone. I mean, it was all the way back in 1799 that someone thought about trying to base a measurement system based on something other than artifacts, based on something in nature, something unchanging. Well, it wasn't quite unchanging. It wasn't quite perfect. In 1954, they added the ampere, the kelvin, the candela. In 1971, the mole. The second was fixed in 1967. And in 1983, the meter was defined by fixing the speed of light. So that is what has happened. I want to point out the idea of fixing Planck's constant and the Boltzmann constant. Of course, it was not called Planck's constant when this comment was made, but you can go read the original paper. Max Planck in 1900 understood this in principle could be done. So it's not a new idea. But it took 100 years from then to have the technology necessary to do it. So it's a wonderful idea. The French Revolution brought us the metric system. Basically, the metric system comes in 1799, shortly after the end of the French Revolution, after they hung their royalty and guillotined them, I guess is what they did, and decided that forevermore, everything should be equal for all people and all times. The Treaty of the Meter brought this into international arena and law. And on the 20th of May, the anniversary of the signing of the 1875 Convention, we will have the biggest revolution, because on the 16th of November, it was voted and agreed unanimously that this would become the new definition of the treaty and the meter. And it will all be done in a way that almost nobody can tell we have done anything. But for the rest of eternity, as long as the people who try to combine gravity with quantum mechanics don't screw us up, we will have a perfect system. Now let me tell you the other side of that. I have just made finding violations easier than ever because it is based upon the best theory we have, quantum mechanics. None of those constants are anything that we don't use routinely every day. So it is really scientifically based. Liberally leading the people means we will finally be free of artifact standards of measurements. All the base units of the system will be defined by fixing values of fundamental constants. Those are the numbers, and I have a few of those cards if you would like them. It is important to realize traceability is directly to the SI. Anybody who has sufficiently sophisticated technology can realize this. Nobody owns it. It's for everybody who has the technology. And we can intercompare and see how well we're doing. It's really democratizing, and it's really realizing what was originally wanted. A set of units for all times, for all people. And so it is great to have been part of this. I have one last thing to show you. And this is a trailer to a movie that will come out later this year. And I will show you this because you can watch what metrologists look like. Come on. Come on. Well, let me escape out of here. I did it earlier today. There we go. Yeah, well, let's see. Go back up here. No, I'll go to the website and find it.
Does this have audio?
Yes, it does.
Let me just put this in the audio jack.
Yeah, I have to turn up. I would do it this way.
I need to plug you in so you have audio from that.
Oh, okay. Go ahead.
Where's your audio jack?
The audio, everything has come to the device. I can turn the volume up. Damn it. Let me stop this again. Technical difficulties. Well, come on. Let's see if I can do this.
Is your system audio turned on? Oh, here we go. Just changed to internal speakers.
Mass mass is still tied to a single artifact in the world.
So I'll start this over. There we go. And we will start.
I feel like our job is to define objective reality.
So that's one of those silicon spheres.
We're trying to get rid of a kilogram. Mass is still tied to a single artifact in the world. Hunk of metal in Paris.
Anything that you weigh from an apple in a grocery store to yourself on a bathroom scale to drugs at a pharmacy eventually goes back to this prototype. It's not enough to work day and night.
Different labs around the world want to find some scientific insight that the others haven't found.
We have only 2-3 months to consider new results. There's a lot of pressure.
That is the last artifact. Thank you.
Okay, so now we'll open up for questions, and hopefully there will be people with microphones ready to run towards those people with questions.
Talk. So a question for you is, you said that you or the NIST purchased this whatever number K.
4,
whatever.
K20.
Yeah. So where do you purchase from, and who
So-
made that?
So basically, you basically agree to the BIPM that you want a new one. They contract with a specific merchant in the UK that produces the platinum iridium alloy that has to be exactly 90% platinum and 10% iridium. It is hardened, shined, pulled into a bowl. It's cut, polished to extraordinarily high standards, and must be within about 50 micrograms of the IPK in order to be a valid artifact. And we will know what that offset is. So, in fact, NIST owns K4, K20, K79, K85, K92, K102, K104, and K105. Yes, I own 8 kilograms. And I won't tell you, I will tell a brief story about, I had one of my staff, we had 4 of our kilograms sitting in Paris. I had one of my staff, I said, just stop by the BIPM and pick up our 4 artifacts. And he says, well, what do I do with them? I says, you put them in a backpack and you put them on your back and you don't take them off. Now, of course, he's carrying a bunch of little papers to explain all the things he's carrying, including managing to get them through customs and border patrol on both sides, because, what are these things? Oh, they're international prototype killing. You can't open them, you can't look at them, you can't touch them, you can't do this, you can't do that. Okay, and everything else. Now, you might think that was enough, but, when you come back in the U.S. and you give your customs declaration form to the customs people and you say that you have $600,000 of platinum iridium, guess what? You go through customs.
Okay, other questions?
Yes.
Well, certainly beautiful for science people, a beautiful, consistent way of defining these quantities. But then there's a commercial world out there that depends on getting calibrated appropriately. And it seems to me that these ways of defining it makes it very complicated to check whether the scale of your butcher is accurate. So you must have an intermediate system where you derive artifacts that you can carry around.
So part of the whole redefinition, and again because mass was dependent on the kilogram, is all the existing infrastructure. I mean, other than for the atomized places like NIST and PDB, nobody else has to change anything. We can still give them a calibration certificate on their kilogram. Having said that, we've actually demonstrated tabletop versions of the watt bounce that are an order of magnitude more accurate at a gram than what you can get from scaling. We've already demonstrated that. We will commercialize that technology to spinning it off to some company or something else, so that in 20 years, you know, when you go buy a Metrological bounce or whatever bounce you do for your chemistry lab, it will probably be a very sophisticated tabletop version of our bounce. And it will never have to have those little masses around to recalibrate or check or anything else, because it will be inherently calibrated. Now, if you want to add its high standard, you have to know the local value of G. You don't want to move a granite block underneath it, and a few other things. But, you know, in principle, if you understand everything, we will have made the technology easier. In fact, we can see the same thing happening on the electrical side. Having said that, let me just say, when you go to do a tera-ohm resistance measurement, we will continue to do it the same way we do. If we are doing 1,000,000 foot-pounds or 4.54 meganewtons of force, we would do it the same way we currently do today. So there's some things that won't change because I don't have the technology to do it. But there are other places where I can see how to put technology in place to replace it. So great question.
How do you measure the local value of G?
So the U.S. Geological Survey basically has markers all over the country. We have a marker on our NIST campus. And so we basically have an instrument there where we can actually validate that we have a little instrument that basically has a falling corner cube. And then we just move that corner cube around and everything else. Now, I'm going to tell you a little piece of largesse around where this is. The room that this is in, this watt bounce is in a buried building. Notice I said buried. And there is 100 part per million gradient of G across it because the room tends to be toward one end of the building where there's this wall of dirt. Don't worry, we mapped out G every roughly 30 centimeters throughout that whole room, so we knew what the value of little g was everywhere in that room. And then we determined what it was at the pan bounce position, which you have to do as well. So a little work. In fact, that's a lot of the work of Dave Newell. He's our local man who measures little g. Little g is easier to measure than big G.
So I'm going to intersperse. I have exactly 2 questions, but I'm going to intersperse mine among the. So I hesitate to ask you this question because it's a Fermi problem which involves guesstimation, and it seems like antithetical to NIST. But I guess the question is what was the calculated economic impact of this change of the kilogram, the artifact, and what would have been the economic impact, let's say in the U.S. from changing part.
So only that shift of 45 micrograms was only seen by our primary labs, but it invalidated their certificates and invalidated all the calibrations they had done in the period of time. So everybody was told, you must come back and recalibrate. Those people who had a requirement by law, if they were outside of it. Now, most of the people, or like I said, it's only the primaries. The secondary labs was typically about, so the secondary labs are about 80 micrograms on a kilogram. None of them would have been able to see it, been within their certificates. So it's only the primaries. The place where this probably comes back in is the area where this is probably most used is in basically the pharmaceutical industry, which producing some very small quantities of special designed drugs. And again, because you cut down, by the time you get to a microgram, there was no real absolute traceability of mass under the old system. On the new system, this is no longer a problem. In fact, because anybody who knows about how you make an atom recoil, you can do that experiment, everybody understands that you can measure today the recoil of an atom to basically a part in 10 to the 10th, which means that I can determine atomic mass to a part in 10 to the 10th. And of course, that is really a yoctogram to a part in 10 to the 10th. So it's about effectively 10 to the minus 30th or 32, 33, depending on what atom, grams. That's not bad, right, for a day's work.
Bob has a question.
I have in my drawer a list of fundamental constants, which gets revised every few years. And so I understand C is now sort of fixed, will never be revised. Is the same true of E epsilon naught, mu naught?
So all I can say is epsilon naught and mu naught today are well defined. On the day of the redefinition, I've screwed them up. And I've screwed them up at a few parts in 10 to the 9th. And I don't think anybody ever does their homework in electromagnetism to a part in 10 to the 9th, so I'm not sure it matters. But I have screwed them up. And you know, you fix one thing, you break something else. Well, that's just the problem, and you forevermore will see, yeah, it's almost 1/4 pi, but not quite, plus a correction.
Maybe other people can give the microphones. Okay. Thanks.
Is there any push by like NIST for the electrical engineers or whatever to redefine from their K90 values with the Joe system?
Electrical engineers. So again, the physical measurement laboratory, I would say about 10 to 15% of my employees are electrical engineers. I have a fair number of them. No, I mean, none of these people are bothered. I mean, again, it will be seen. Let me just say, the average person in this room should save about a penny on their electric bill next year. Say thank you, NIST. Oh, not very much. The places that will see this is very small. Actually, there was a much bigger problem. Most of you had those old power meters on your walls with the wheels on them. And of course, when they came around and they upgraded these to smart meters, most people noticed that their bill went up. Well, it wasn't because the meters weren't originally calibrated. They were. But any mechanical object, if you leave it long enough, it eventually slows down. Why? It's just called friction. And, you know, been on your house for 40 years. Nobody's ever come back and checked it. And so when they put the smart meter on your house, oh, NIST got dragged into that big mess too. Cleaning that one up was fun. But those are the esoteric kind of things that you see.
So what's up with the candela? I mean, I know you didn't say very much about it, but
so like, the candela is.
Does anybody care?
The lighting industry cares. The people who care about human perception. The candela really is how our eye response views light, and it was created to take exactly that response in. So it's the only one that's really is based upon the human condition. Having said this, I believe that probably within 20 years it will be gone. Why? Because what we will do to redefine optical power is we have basically been working at NIST to demonstrate that I can count photons all the way from 1 to an Avogadro's number of them. In fact, we did an experiment this past year down at White Sands where we were looking at high-powered lasers. You can imagine what those high-powered lasers are used for. We created the original calibrating spheres and everything else, and we could show you the big room that you would take to calibrate those in the old days, and I'd absorb all your laser power, heat it up, measure the heat. And we told people, look, we don't need to do that. We will calibrate your laser power and we will give you back your laser. And they said, you can't do that. And yes, we did. All you do is you just take that power, you put it on a really, really black mirror. That is one made with nanotubes and other things, highly reflective. You measure the momentum impacted by all those photons bouncing off the mirror. You weigh it. And I can tell you how many photons that were there. And moreover, I've given them back to you. That technology is being commercialized, additive manufacturing, and other things. So again, we today are basically in the process of being able to go from one photon all the way up, be able to count them, and create a true scale all the way up. So eventually, I think it will go away because it really is a useless.
You said it, not me. Okay, maybe I did say it.
I noticed you didn't mention anything about Boltzmann's constant this entire talk. So, well, why do you hate Kelvin? And also, what impact does it have?
So don't hate Kelvin. I mean, the Boltzmann constant, there were numerous efforts to basically measure the Boltzmann constant around the world. There were probably about 8 or 10 different experiments worldwide, most of them using acoustic gas thermometry, but there were two other techniques also used, Johnson noise thermometry and what was the other one? Oh golly gee, now I can't remember. But those efforts were underway. The reality is that you might think we have a temperature scale, but what we actually run with is a temperature scale that is a set of fixed points that are not quite on a straight line. And that temperature scale has been agreed to. And what was done by fixing Boltzmann constant was the ability to just get away from having these fixed points and actually having a true linear scale. And now you can tell me how well you can actually realize temperature on that linear scale. So, and we've already begun commercializing some solutions out of that space as well. So again, there are technical solutions to all this stuff. I mean, that are really quite remarkable, and it's really what took all the time to get to the redefinition is really developing the technology to a level that nobody could see that we are messing with the underlying system. Because part of the condition under which you can change the treaty is that most people can't tell. So all we did is just come back in and put a firm foundation under it. And so the Boltzmann is as important as any of the other units. And NIST contributed to define the Boltzmann constant. We weren't the best on that one. I think the UK and Germans were the best.
Okay, let's thank Carl Williams again.